Hello, good afternoon everyone. My talk is entitled Influence of Nominal Composition Variation on Phase Evolution at Grid Life of 316 austenitic stainless steel. So I have organized the talk through different sections. I will start explaining the motivation and the background of this research to focus on the main objective of this exercise. Then I will go through the experimental techniques and materials. I will show some results and I will end up with some conclusions. So let's go with the motivation. To cover an energy gap in the UK, the life of a generation of advanced gas reactor had to be extended over their design life. So in this scenario, the integrity of some components made of 316H austenitic stainless steel, such as headers, boilers, pipe and tubes, is crucial. So it's so important to understand how those components age under load and how the composition influence such aging, to include all of this knowledge into the creep life prediction. So the creep lifetime prediction depends upon different factors, such as the deformation and damage mechanism operating, as well as the primary stresses and residual stresses. But of course, it depends on the creep deformation constitutive model chosen to predict this creep lifetime. But on top of that, we also have to take in account the material microstructure, how this initial material microstructure ages during service, and how the composition affects those changes. So we know that in 316H austenitic stainless steel, secondary phases appear during aging. The number, the density, and the type of those phases can be quantified either experimentally or using computer calculations, and the results may show the kinetic or thermodynamic state of the samples. But we also know that the secondary phases affect the creep life in a way that intergranular secondary phases modify the creep failure by creep cavitation formation. And also intergranular secondary phases also modify the creep rate by creep deformation. So we have some TTP diagrams, time temperature precipitation diagrams, showing this kinetic evolution of the precipitates. But the problem is that we haven't got a lot of data for longer aging times. So, as you may guess, the main objective of this research was to compare three steels, but with the same nominal composition, to understand if there was any statistical differences between the samples, to see also if there were any differences in the percentage of secondary phases M23C6 and alpha ferrite, and compare those values with the thermodynamic calculation using thermocalc. So let's go through the material. So we received three samples from EDF. The three samples were made by the same time for the three different steel makers. So we call them A, B, and C. The three samples had a nominal composition of 316H austenitic stainless steel and were aged during 150, 145, and 300,000 hours at about 500 degrees. The microstructure was homogeneous with a grain size of 50 to 100 microns in diameter. However, sample A saw a lower hardness than the samples B and C, and also sample A was found to be more prone to creep cracking during the aging, during the service, in the heat affected zone. So we use electron probe microanalysis to measure the composition of the three samples. Then we prepare TM foils using ion milling by the technique leave out, and then we analyze the TM foils using the geo-arm transmission electron microscopy. We identify the secondary phases, and also we quantify the percentage of M23C6 and alpha ferrite using electron backscatter diffraction. At the end, we calculate the percentage of those secondary phases in the equilibrium using the thermocalc version 2015B and the base data TCFE steel iron alloys. So let's go through the results then. In this table we can see the bottom line with the specification of the 316. We measured the composition of the 3 samples, and as we expected, the composition was within the specification. But we found the major differences in the elements silicon, nickel, and manganese. But I would like you to remember that sample A saw a lower content in silicon and also the higher content in phosphorus. But we went a bit further. We wanted to compare the samples statistically. And then for this, we used a parametric statistics test, which required to have the data normalized. And then we proved that the data was normalized in this table at the bottom. And then we compared element by element, the 3 samples, using a multiple comparison test. If we see in this table, the top one, only chromium between sample A and C, and iron and moly between samples B and C were significantly similar. The other possible combinations were different, so we can say that the samples actually were different in composition. We also prepared the TEM foils, and I show here just the example of specimen A, because I haven't got more time to show all of them, but we found out the same 3 types of precipitates. We found really silicon-rich phase, potentially G phase. Then we found chromium-rich, but iron-depleted and nickel-depleted phase, and was found to be M23C6. And we found alpha ferrite within these samples with enrichment in iron and depleted in chromium and nickel. We found the same type of precipitates in the 3 samples. However, we also measure at the image the interfaces between the precipitates and the metrics, and we found out that only sample A presents phosphorus segregation in the interface austenitic M23C6. In the other 2 samples, in B and C, they didn't show any phosphorus segregation. However, they show an enrichment in phosphorus in the silicon-rich phases. If you remember that I said that the sample A had a lower content of silicon, we may say that silicon play an important role in this phosphorus segregation. And this is why maybe samples B and C didn't show any phosphorus segregation. If we go now through the percentage of secondary phases experimentally measured and the calculation, we see in the first table that the amount of secondary phases is different within the samples. We can be also explained because of the different composition between them. Finally, the thermocal calculation doesn't match with the experimental results, which makes sense because by the temperature that the sample was 8 and the time scale that the sample was removed from the service, the equilibrium wasn't reached yet. So, regarding the implication with the creep life, back in 1983, Dyson proposed a relationship between number cavities and number precipitates. However, this relationship is not as simple because it depends on the type of precipitates and the interfacial energy between them. So anything decreasing the interfacial energy will promote the creep cavitation. And this is why, for example, phosphorus may promote this creep cavitation in sample A. As some conclusion, we may say that the 3 samples made with the same 316 austenitic stainless steel and therefore same nominal composition result to be statistically different, and then such differences may explain why they have different content of secondary phases. Experimentally, we have seen that they have the same 3 types of secondary phases, M23C6, G phase, and alpha ferrite. But silicon may play an important role in controlling this distribution of phosphorus. And this is why sample A or steelmaker A had a shorter creep life. Thank you.